Hello, welcome back. I'm Mario Lopez, part of the organizing team of this event. Now I'm going to present the next speaker, is Nerea Palacios. She's a chartered engineer working at NIRAS. She studied civil engineering at Burgos, Spain, and completed her studies at the University of Southampton. She's specialized in ports and maritime infrastructure, and she's presenting construction challenges during a worldwide pandemic in the remote Shetland Island. So Nerea, the floor is all yours.
Thank you, Mario. Hello, everyone. My name is Nerea Palacios, and I am a chartered maritime engineer based in the United Kingdom. In today's presentation, I want to give you an insight into the construction challenges I came across during my site supervision at Tough Pier in the Shetland Islands. But first, a little bit about myself. As Mario presented, I currently work for NIRAS, which is a Danish engineering consultant, although we work in projects all across the globe. I have 7 years of experience in the design of a wide range of maritime facilities, including quay walls, dry docks, moored dolphins, jetties, and slipways, among others. I've also had the opportunity to be based on site on several occasions, carrying out inspections in a container terminal in the UK, and also supervising the last stage of the construction of Tough Pier, which leads me to today's presentation. So my presentation today is about my site supervision role in the last stage of the construction of Tough Pier in the Shetland Islands in Scotland, which I undertook during 6 months in the winter between 2020 and 2021. The image you see on the screen is an aerial view of the pier during construction on a calm day. And hopefully in the next 25 minutes or so, I'll give you an overview of the structural design approach of pier, the construction process, and the multiple challenges that we face along the way. So first of all, let's locate Shetland Islands on the map. Shetland Islands are located in the northern Atlantic Ocean. They are between Great Britain, the Faroe Islands, and Norway. They are the northernmost part of the United Kingdom, approximately 170 kilometers away from mainland Scotland, and have a total population of around 23,000 inhabitants. This pier in particular is located in Toughs Bow on the northeast coast of mainland Shetland. And the islands are characterized by much more than just the remoteness. They have a very rich culture, a vibrant society, and a dynamic economy that makes Shetland a very interesting place for NIRAS to operate. Unsurprisingly, fishing is a very important part of the local economy. And as a result, access to ports and marine infrastructure across the islands is of vital importance to the local communities. NIRAS helped design and develop a new pier in Toft for the local fishing community and aquaculture industry. So the new pier provides approximately 100 meters of quay length and replaces the former existing pier that we can see on the image on the left. The extension of the pier provides more berthing space for boats and better shelter in poor weather. The new pier is approximately 3 times larger than the old jetty and provides around 1,100 square meters. It also offers vessels an increased water depth on both the inside and outside of the pier. Some quick facts. Shetland Council decided to upgrade and extend the existing pier and appointed NIRAS as the principal designer through an ECC Option A contract. NIRAS completed the design in 2019, and the demolition of the existing pier started later that year. The main contractor was TMS from Devon in the United Kingdom, although multiple subcontractors were involved along the project. The contract value was £3.5 million, and it was partly funded by a grant from the European Maritime and Fisheries Fund. So here we can start hinting one of the challenges that I will address later on related to the United Kingdom leaving the European Union and the problems related to the funding. The new pier is a double wall cover dam structure comprising two parallel lines of seed piles connected together by tie rods and filled with crushed rock in the middle. The main elements to be designed by NERAS were the A-site set pile walls, the tie rods, reinforced concrete capping beam on top of the piles, reinforced concrete slab, dredging, and also the port furniture, which included things such as marine fenders, bollards, ladders. Also services such as water, electricity, CCTV, lighting were also included in the scope. And finally, cathodic protection was also provided to reduce the corrosion in the seed piles. My responsibilities as the designer's representative on site included ensure compliance with design drawings and specifications, resolve any potential contractors' queries on site, approve materials and PR elements. I also had to ensure good construction practices to guarantee a good quality finish, and last but not least, supervise health and safety on site. The existing pier was originally built as a ferry terminal in the 70s and had reached the end of its serviceable life. As you can see on the image, it was in a state of disrepair and had been out of service for several years before it was finally upgraded. For the demolition of the existing pier, temporary pontoons had to be removed, as well as the small port building, the existing surfacing, the deck furniture, things such as ladders, bollards, fenders, handrails, lighting columns. All of that had to be demolished. The existing structure was locally dismantled or demolished as required to facilitate the construction of the new works. However, the existing seed pile walls and concrete capping beam were mostly left in place, although they don't have any structural function. It was just cheaper to leave them there. A-set seed pile walls were embedded 5 meters into the seabeds and connected by M85 tie rods that were installed roughly every 5 meters at mean high water nip. The total retained height of the walls is approximately 9.5 meters, and the installation process of the seed pile walls consisted in placing a guide frame or guide beam on the ground to set out the position of the wall, and then the piles are driven into the ground with a vibro hammer. During the piling operations, it was reported that some piles along a short section of wall could not be driven to the design toe level. This was possibly due to an existing concrete scour mat or maybe a big boulder, as boulders were identified in the geotechnical investigation. And as a result, they had to mobilize a long reach excavator with a rock breaker on the end, as we can see on this video. And unfortunately, this incident led to a 3-week delay in the program. The next step after the installation of the piles was filling the inside with self-compacting granular fill material. And after that, they constructed the concrete capping beam that goes on top of the piles. This is approximately about the time when I moved to Zetland and I started supervising this project. The capping beam is 900 by 175 mil, and it's made of C40-50 concrete. The construction started with the installation of the reinforcement, followed by the timber shutters. And on this image, we can also appreciate stainless steel dowel bars that connect the capping beam to the concrete slab that will go later on. This is to avoid the potential differential settlement, since the capping beam sits on rigid piles, whereas the slab sits on backfill. Next, the capping beam is poured with concrete. In this case, they use a skip moved by a crane to pour the concrete. They use a 200 mil slam concrete, which is quite high, but it needs to be in order to ensure the concrete fills all the volume in the shutters, which is also achieved by a good vibration. The surface was given a brush finish to get a good grip. And finally, once the concrete has hardened, the shutters are struck. And this is how the final capping beam looks like. Again, on this image, we can see the stainless steel dowel bars that connect two sections of capping beam next to each other. But I will talk a bit more about the joints later on. There is an interesting detail that I thought it was worth highlighting, is the connection between the reinforced capping beam and the seat piles underneath. On these images, we can see that a welder created these slots at the top of the piles so that the rebars of the capping beam can go through. And in this way, they achieve an adequate concrete cover, and there is also a good connection between the two elements. Before placing the concrete slab at the top, they excavated trenches to locate the services, mainly water pipes and electric ducts that provide the pier with water points, but also street navigation lights, and even a landing crane that will lift the fish boxes to and from the vessels. Then the trenches are backfilled, and the different sublayers that go under the slab are put in place. The sublayers included a geotextile above the fill material, a granular subbase, followed by an impermeable polyethylene sheet, and finally, a layer of blinding at the end. The reinforcement of the concrete slab is then laid on top of the blinding layer, and the concrete is poured with a skip moved by a crane. For the slab, they use 160 mil slab concrete, which is drier than in the capping beam, because in the slabs, the concrete needs to be able to have a fall for drainage purposes, so a very wet concrete would not work. The surface is smooth and level with a spin roll, as we can see on the central image, and finally, it is brushed to get a good grip. The slab was 275 mil thick and was made of C4050 concrete. The structure had several movement and expansion joints between adjacent sections of capping beam and slab, and also between the capping beam and the slab. They used stainless steel bars at the joints, and in the case of expansion joints, half the length of the dowels was covered by a debonding slip, and there was a compressible material at the end to allow for the expansion. Moving on to the port furniture, there are different types of fenders in this pier that correspond to different sizes of vessels. There are fenders made of tires for the smaller vessels in the inner face of the pier, and also more robust systems consisting in element and cylinder fenders, as we see on the second image, for larger vessels on the outer face of the pier. Ladders are located every 9 meters, depending on the location, and they are protected from vessels' collisions via timber fenders. This is the same spacing as the horn bollards, which have a capacity of 30 tons. And in addition, recycled plastic curbs are also provided along the edges of the pier to prevent accidental falls of vehicles into the water. The port furniture also includes landing crane to load and unload cargo onto the vessels. And the crane foundation consists in a thickening of the deck slab, as we can see in the first image. The crane is able to lift a ton at 7 meters. And at this point, I want to show you the 3D model that was created for this project, where we have a clearer vision of all the elements that form the port furniture and the dimensions. So I'm going to try to share my screen. Hopefully you can now see my 3D model. So this is a 3D model that was created for this project. Here we have a clear vision of all the elements, the geometry, and all the parts of the walls that were involved. So if we focus first on the outer side of the pier, we can have a look at the marine fenders. We have horizontal element fenders and vertical cylinder fenders. This outer side of the pier is deeper. It is designed for bigger design vessels, and therefore a robust berthing system needs to be in place to absorb the berthing energy coming from those larger vessels. We can also see the ladders, the recycled plastic curbs, the horn bollards, and all the street lights. This side of the pier on the left-hand side is shallower, therefore the design vessels are smaller, and there is no need to have such a robust fender system. Therefore, tire fenders, as we can see in this image, are sufficient to absorb the berthing energy. If we turn around the model to have a look at the inner side of the pier, this inner side of the pier is also shallower, therefore it is envisaged for smaller design vessels, and as you can see, there are sets of tire fenders to absorb the berthing energy coming from these smaller vessels. Although it's not included in the model, the landing crane is currently sitting somewhere here in the corner. And if we create a cut of the model, we can even have a look at the insides of it. And here we have a clear vision of the tie rods, the parallel lines of seat pile walls, and how they are connected together thanks to these tie rods. So just a little model I wanted to share with you. So I will stop sharing, and if we could go back to the presentation. Thank you. So moving on to dredging. To ensure the access of the design vessels, the inner side of the jetty reserved for smaller vessels was stretched to -5 and the outer side to -6. The equipment used to dredge the seabed consisted in a long reach excavator mounted on a pontoon that rests on the seabed by hydraulic legs. And the dredged material was then unloaded in barges moored to the pontoon and later disposed into an approved landfill via lorries. The pier is provided with a cathodic protection system to minimize the corrosion experienced by the seat pile walls. The cathodic protection system was designed by others, but the principle is that the metal to be protected is connected to another sacrificial metal that is more easily corroded. So this corrodes first instead of the seat piles. On this image, we can see the sacrificial anodes that were welded onto the seat piles by divers. Cathodic protection only protects the area of seat piles that is permanently submerged, though. So the seat piles were also coated with a coating layer to minimize their corrosion. Moving on, there was a number of challenges that we faced along the duration of the construction. The challenges included the remote location of the site, the presence of an operational busy ferry terminal next to the site, rough weather, technical challenges, the environmentally sensitive nature of the site, Brexit, and the pandemic, to name a few. Some of the more technical challenges that we face on site included, for example, the dredging operations. According to the GPS system of the contractor that undertook the dredging, they thought they had dredged the seabed to the required depth. However, when a survey by a third party was done later on to check the depths, the survey revealed the depths were shallower than required in certain areas. So as a result, the contractor had to come back to site to do some extra dredging in those areas until the required depths were finally achieved. Another technical issue that came up after the pier opened to the public was regarding the fenders. It was noted that some boats with low freeboards were stuck under the horizontal element fenders at low tide. This is because originally the outer face of the pier, as I've explained in the 3D model, was where these element fenders are, was designed to accommodate larger vessels with larger freeboards. But in practice, the pier was used mainly by smaller boats than those it was designed for. That's the reason why they were getting stuck. After some calculations, it was concluded that the vertical cylinder fenders were sufficient to absorb the berthing energy coming from most of these smaller vessels that were using the pier. So the element fenders were removed, although they can be installed back if needed when these larger design vessels are actually using the pier. Talking about other sort of challenges, and the site was located next to a busy ferry terminal that was also designed by NERAS. The terminal connects the main island with a group of smaller islands farther north, and it had a constant flow of vehicles coming in and out. There was also a bus station just outside the site, so sometimes it was challenging to minimize the disturbance to normal traffic, especially with heavy construction vehicles, such as the trailers that carried the dredging barges and that we'll see in action in the next slides. On top of that, the later stages of the construction of the pier took place during the COVID pandemic. The outbreak of the pandemic led to delays in the program, difficulties to travel in and out of Shetland, and the search for ways to keep everyone safe on site. Some of the measures adopted included daily checks of body temperature and social distancing. However, the good cooperation with the Shetland Island Council and the contractors on the projects made it possible to minimize the disruption and still deliver this valuable facility for the local community. Working in such a privileged environment was an incredible experience that I don't think I will ever forget. That sense of remoteness and wildness makes Shetland a very special place. From this pier, I have seen killer whales, otters, seals are everywhere. We can see one next to the barge that was used for dredging in this picture. Another role NERAS had was marine mammal observer to implement mitigation measures and protect marine life during the construction operations. But at the same time, the environment is also tough. Heavy rain, winds of up to 100 miles per hour, extreme tides. All these conditions, as you can imagine, made the construction works very challenging. Due to unforeseen delays in the license process, the works at Tough Pier did not start until August of 2019, and this pushed the piling operations into winter. As expected, this is not ideal in the windiest place in the UK. In normal conditions, piling would have been paused until the summer, but there was a fast approaching deadline to complete the pier in order to secure the funding that was coming from the European Union. And the UK were in the process of leaving the EU, so the piling had to go ahead during winter. There were significantly strong winds during piling operations, snow during the concreting operations. But having said that, I do believe these extreme conditions contribute somehow to the magic beauty of this place. Following on the rough weather conditions, Shetland is a group of islands that largely depend on the supplies that arrive by boat from the mainland. When the sea is rough, the ferry services to Shetland are suspended, and therefore there are no supplies. So this image on the left shows the empty shelves in a supermarket in Shetland after several days of rough sea. Usually these periods of extreme weather only last for a few days, and in any case, local shops tend to be well stocked with local produce, so nobody's going to starve. But the remoteness of the site is undoubtedly an additional challenge. Not only there are delays in food supplies, but the delays also affect construction materials and equipment. The barges that we can see on this video are the barges that were used for dredging the seabed. This is when they were leaving the site, but they did an interesting journey to get here. They were transported by road all the way up from Devon in the south of England, and then loaded onto carrier ships to be delivered to Shetland. It's not difficult to imagine the magnitude and difficulty of such a transport operation. It was very impressive to even witness it. The pier was finally opened to the public in May 2021, and it has been very well received among the local communities and the users of the pier so far. So here there is a quote from Alistair Cooper, chair of the Development Committee of the Shetland Island Council, highlighting how important this infrastructure is for the local community. Coming to the end of my presentation, the delivery of this project further strengthens the client relationship of NIRAS with the Shetland Island Council, which already spans for 50 years. And during this time, NIRAS has been responsible for the design, maintenance, repairs of a series of maritime infrastructure in the Shetland Islands. And this leads me to the end of my presentation. Thank you for your attention, and I hope I have provided you with an insight into what the site supervision in a marine environment is like. And now hopefully you can locate the Shetland Islands on the map as well in case you couldn't. So if you have any questions, I will do my best to try to answer them. Thank you very much.
Thank you, Nerea. Thank you very much. Congratulations for your presentation. I think you have a quite singular experience there. Okay, let's move to the question. We have one here. Are there any, from Rodrigo, sorry, are there any particular challenges from a personal perspective of working in such a remote location? I imagine that the logistics are not so easy.
Yes, absolutely. As we mentioned in the presentation, one of the challenges is the remote location of the site. So getting in and out of Shetland is kind of a challenge on itself. Especially during my time there, we had the COVID pandemic ongoing. So the traveling was very restricted and very difficult. On top of that, in Shetland, we have the rough weather. It's not unusual that flights are canceled or ferries are suspended. So getting in and out is a challenge in itself. I personally live in the south of England, so it was quite a journey to get there. But as I said, I think to me, the remoteness of Shetland is part of its magic and its charm, and it's what makes it special, I think.
Okay. Okay, I think we don't have more questions. So if you want, we can have a break of 10 minutes and let's come back in 10:30 in Brussels time. So thank you very much, Nerea.
Thank you.
Congratulations. Thank you. Hello, welcome back. Hope you are enjoying the event. Next speaker was Nathaniel Bulbo, but unfortunately he cannot make it today. He will be replaced by Sei Singh, who is involved also in the topic. Sei is a coastal and maritime structural engineer working at Hatch Ports and Terminal Australia and Asia team with Nathaniel. He has a background in ocean engineering at university in Australia and has experience in maritime structural engineering, which is a result of his involvement in the design and several maritime structures at a variety of ports. So Sei, the floor is all yours.
Awesome. Thank you for the introduction, Mario. Hi, everyone. My name is Zay, and I'm a maritime and coastal engineer working at Hatch, Brisbane, Australia. And thank you for the disclaimer, but I'd like to repeat it. So I'm not the original presenter of this topic, which is listed in our flyer. I'm actually one of the YP organizers of this conference. Unfortunately, the original presenter is no longer able to present this, so I'm presenting on his behalf. It's been an interesting situation. I've had less than 2 days to prepare for this presentation, so hopefully it go a bit easier on me. So without further ado, let's get into it. I'll be presenting today about assessing and strengthening aged timber marine infrastructure. Just about all of the clients we work with who own aging maritime assets try to get as much service life as possible out of them. In some cases, they seek to extend their asset service life past the original design life. As engineers working in the maritime space, this poses us with the challenge of dealing with brownfield facilities that are in various states of degradation. These facilities were also likely designed to supersede or less stringent design code. We actually picked this topic because a lot of the work we do at Hatch, or some of the work we do at Hatch, is focused on the rehabilitation of existing marine infrastructure. So for today's agenda, I'll start with going through a bit of the brief historical overview of timber use in maritime structures. Then I'll go through some typical deterioration mechanisms, method of inspections, and then finally some remediation solutions that can be adopted for various circumstances. So for the historical overview, timber has traditionally been used for the construction of a wide variety of engineering structures in or near water, including groins, jetties, lock gates, and river bank protections as shown in those pictures. Timber structures are located in many of our most valued and precious environments, and the suitability of it is demonstrated by its use in both traditional and contemporary structures. One of the most significant uses of timber in coastal and river engineering is for groins to interrupt the flow of the water and to limit the movement of the sediment. Many of these groins are aesthetically pleasing, as well as being efficient, effective, and environmentally responsible. So despite advances in alternative materials, timber is still used for some applications in the maritime industry due to some generally accepted characteristics. These include the fact that they are renewable and environmentally responsible material. They have a high strength to weight ratio. They have a high tolerance of short duration shock loads, good resistance to abrasion, good walkability, and ease of modification, repair, or reuse. They also have aesthetic appearance and have natural durability. But of course, there are a number of potential drawbacks of using timber in the maritime environment. And these drawbacks are one of the main reasons for this presentation, expanding on methods of remediating timber that has deteriorated. These drawbacks include inherent flaws and variability in properties. There's also limited availability for very large section sizes. They're naturally durable, but in the maritime environment, it's a slightly different scenario. They're also susceptible to biological hazards such as termites and marine borers, and they are only renewable over a relatively long timescale. I'd like to expand a little bit more on the renewability aspect of timber, given the current global trends and the importance of sustainability. I think it's quite important we talk about it. Timber has the potential to be an environmentally responsible choice of material if recycled or obtained from sustainably managed forests. It's virtually carbon neutral, emphasis on the quotation marks because that doesn't account for the transport and processing. But other than that, it is carbon neutral, and it also has low embodied energy. In addition, all forests sequester carbon from the atmosphere, both in living biomass and in forest soils. It's important to note that there is concern regarding the degradation of forests while using timber as a construction material, but most types of these forests can be managed sustainably and pretty much harvested periodically in a way that their productive benefits for future generations is not compromised. However, to achieve this, issues such as illegal logging, wastage, and deforestation must still be addressed, but we should also note that many alternative materials are also just as damaging to the environment as timber, if not more. So moving on for the overview of timber, we'll discuss some of the deterioration mechanisms of the material. I won't be addressing every single deteriorating mechanism, but I'll present the primary ones we've seen from our experiences. The first one is the splitting of timber. So over time, timber sections may split, and this is commonly due to the changes in the moisture content from when it was installed. They can be also caused through the usage of unseasoned timber in construction and through the wetting and drying caused by the marine environment. So according to the Australian standards, AS 1720.1 to be specific, most timbers can shrink up to 0.3% in direction of parallel to the grain and up to 10% transverse to the grain. Splitting can also occur due to high stress concentrations at connections caused by both permanent and live loads. If you believe the timber section you're dealing with may be susceptible to splitting, or splitting has already occurred, installing split rings may restore integrity to the section or at least minimize further degradation. So rotting and bacteria attack is another method of deterioration. As you can see in that picture over there, that's from a site we recently went to. Rotting of timber elements is a very common type of deterioration, usually the easiest to identify from a visual inspection. They also occur due to the wetting and drying of timber and the moisture providing environment of growth for the bacteria. So this will typically be seen within the tidal zone. However, depending on the durability of the timber, it will occur throughout the extent of the pile submerged in water. The affected timber will soften up and eventually disintegrate. The softened area would have a reduced material density and hence less structural capacity to resist design loads. Therefore, it's important to understand how much section thickness that exhibits the original design density is left. Now, another leading cause is termites burrowing through the timber and creating nests. The termites are seeking protection and they feed on the timber as well. In maritime infrastructure, we typically see this for superstructure elements, such as on the underside of headstocks, because they're connected to the landmass and provide a way for the termites to get there. Sometimes it's difficult to see a termite attacks occurring until it's too late. As shown in the photo on the screen, you can see a termite nest, but however, it would have taken quite some time for it to be built up. So the termites have been likely living inside the timber elements for quite some time by the time you see a big nest. And they can actually cause, a loss of the structural cross-section as well as collapsing of the load-bearing beams. Now, marine borers, they're also another mechanism of deterioration. The small invertebrates, commonly mollusks or crustaceans burrowing into the timber. They're very dangerous, and as they occur internally, often you can't even see what's happening until it's too late. They can enter the piles from within the tidal range, or they can even start from the seabed and travel up to the pile. If that has occurred, the damage has already begun, so any sort of remediation will be a lot more costly because you need to repair a longer length of pile rather than just the area within the tidal range. The borers will cause a loss of structural cross-section and may even cause the disconnection of the pile from the socket. So that was the primary deterioration mechanisms we've observed based on previous inspections. So we'll move on to what methods we use to carry out these inspections, starting with the most simple and entry-level one, measuring the circumference of the pile. This process is pretty simple and involves just measuring the circumference of maritime piles at different spots to investigate whether section loss has occurred. Measurements are achieved by using a vessel that's capable of maneuvering to and between the piles or via underwater inspection. If you use a vessel, it's relatively low cost, but you're limited to inspecting within the tidal window. Using underwater inspection means you are no longer limited to this and you can obtain an increased sample size and results. However, it is underwater, so it requires divers and it is a higher cost. And it's also likely that there's marine growth on the piles underwater, so the divers will have to remove or scrape them off before measuring the circumstance to obtain accurate values. So we can also inspect piles through resistance drilling and bore scopes. This process involves drilling into piles to determine how sound the remaining timber is. This is typically undertaken at high stress areas and is a destructive method of testing. So TMR, which is the Queensland Department of Transport and Main Roads, provides some guidance on where to drill for bridge piers, and we can actually apply this to maritime piers as well. They recommend using a 12mm drill bit and to drill at 500mm intervals for members which are evidently deteriorated. Advantage of this method is that it confirms both the presence of marine borers as well as the effective remaining cross-section. The drawbacks are that it is labor-intensive and a destructive method of inspection. In contrast to this next method is a non-destructive method of testing and has a few names to refer to it by. For simplicity's sake, I'll just refer to it as the sonic echo method. This method involves measuring the acceleration of wave energy after sending a pulse or wave down the length of the pile. Wave reflections occur at irregularities such as cracks, voids, and pile terminations. A receiver then measures the variation in this wave acceleration and then integrates the output of the wavelengths to determine the particle velocity. We recently got to see this method being undertaken by a specialist geophysical inspection company called the SSA. We used the data outputs to refine our assumptions around the residual pile condition on a recent project. The sonic echo method is quite an effective and diverse method for testing material thickness. This method's not limited to wooden piles and can also be performed in both concrete and steel piles as well. So this slide shows a typical type of the output we were receiving from the specialist company. A magnification factor is applied to the raw wavelength data to enable data interpretation towards the bottom of the pile. From this, a cross-section elevation can be developed, showing the remaining cross-section area of the pile, along with the location of where the pile terminates. Overall, the sonic echo method is a very effective method to use for pile inspections. It's quick, cost-effective, and provide information on both remaining thickness and the termination level. The time taken to test each pile is also pretty minimal and takes around 10 to 15 minutes per pile. The disadvantages are that in some cases, refractions are unable to distinguish between external section loss or marine borer cavities. An easy solution or workaround around this is to benchmark some of the pile testing with resistance drilling. So in circumstances where a protective layer covers the pile from visual inspection, such as a concrete sleeve, as shown in that picture, or tape wrapping, the sonic echo can still provide a reading of the pile condition. The case shown in the picture, we initially assumed that this pile has minor defects given the condition of the visible extent of the pile. In fact, the pile has deteriorated within the concrete sleeve to the point where it has lost the majority of its socketed length in the soil. So once we've identified the deterioration mechanisms through inspections, the next step is to find remediation solutions for the pile. Similar to previously, I won't be able to explain all the remediation solutions, but I'll talk about the primary ones we considered for our projects. So the first one is wrapping piles in tape to provide a protective barrier. The solution is probably one of the most cost-effective solutions for pile remediation out there due to the low installation costs. The solution also minimizes exposure to rotting and marine borer activity in the tidal region. The main drawback of the solution is, of course, it doesn't really facilitate the restoration of pile strength. It also prevents future visual inspections, as the wrap would have to be removed before inspecting again. Also doesn't really protect against marine borers entering from the seabed, only prevents them from entering within the tidal region. So another solution we've identified is pile jacketing. This pretty much involves installing a jacket around the pile as shown in the sketch on the slide. I made it this morning, so please take time to enjoy the sketch. After installing the jacket, the annulus is filled with grout and even potential of reinforcement being installed with the grout as well. As you can see in section 1.1 of that sketch, the ends of the jackets are connected together by either bolting them together or even welding them together. The solution may restore the load-bearing capacity of the pile, but ultimately they'll depend on the final detail of the jacketing solution. Additionally, it also protects against further degradation due to rot. Now, the disadvantage of this method is similar to pile wrapping. It is not able to stop future marine borer activity. This method is labor intensive, but not as labor intensive as our next remediation solution, which is the final one we will talk about today. So the final remediation solution that we'll talk about is pile splicing. The way it essentially works is the defected pile is fully removed, just simply cut out, and then the new section is spliced and bolted to what is left of the existing pile. It's to be noted that the number of bolted splice connections in my sketch is just indicative. It could be a lot more than 4 piles as shown on the screen. The pros of this solution is that it restores pile strength. If we're modeling this in a structural analysis software, you could model it as one continuous member. The cons of this solution is that it is a high-cost solution. There's a significant amount of on-site work required to achieve this. Cool, that brings us to the end of my presentation. Hope you guys enjoyed it. If you have any questions, please leave them in chat and I'll try my best to answer them. If I can't answer them, I'll direct these questions to my coworker who was meant to present this. Thank you.
Thank you so much, Sei. Congratulations for the presentation. It was very interesting, and thank you for replacing Nathaniel. Before the question, we are going to release a poll in the platform, so you as attendees can vote who you consider is the best speaker of today's session in terms of topic, presentation, and relevance. So you can vote, and now we can move to the questions. So if you have any question, you can type it in the chat. Let's wait a couple of minutes. So it seems we don't have questions, so we can move to the closing words. So now I'm proud to. Sorry, there is one question. Sorry. From Andrew, if you were designing a new wharf today, would you consider using timber piles?
Great question, Andrew. Thank you. Most likely not. Most of the new wharfs we design are using concrete piles, steel piles. We would consider using timber piles if it was a project that was a lot more focused on the aesthetics of the wharf, or maybe it was a low cost, or a wharf that would not take as much load bearings. So for example, for berthing of smaller vessels or a private wharf, sure.
Okay, thank you. So yes, I think we can move to the final word. So now I'm proud to present Francisco Esteban Lefler. He's the president of PIANC from 2019. He studied at Madrid Polytechnic University and he has worked in Puertos del Estado, FCC, and now as an independent consultant. Francisco, thank you for being with us today.
Okay, thank you very much. Good morning, afternoon, etc., according to the different parts of the world. Well, after 2 intense days of high-level presentations from all continents, I must congratulate all the organizers, including the work by PIANC, YPCOM chairman Sebastián Iglesias and YPCOM board, Rocío López Velasco as chair of day one and the chair today also, the all session chairs, authors of the papers and presentations, attendants, mainly those who ask questions, of course, and of course the winners of this international contest. I wish all you will try to join PIANC activities, and being young professionals, I encourage you to present papers to the prestigious De Pape-Willems PIANC Award for Young Professionals. This award has been an important boost for many careers, and former De Pape-Willems Award winners are today professors, corporate managers, and high-level experts. We are in interesting time in PIANC. In the after-pandemic period, we are recovering our physical events. As you know, PIANC has 2 main lines of work. Our famous working group reports that are a worldwide reference publications developed by our commissions, and the main PIANC events as the World Congress, the Smart Rivers Conference. Last one was still a hybrid conference because of the particularities, and the COPEDEC, and returning to be physical, providing opportunities for networking that is very, very important in our association. Many regional and national events are also returning to physical. However, this does not mean that we will put aside virtual events. Of course, this is an excellent example. We have learned a lot about the opportunities that online events mean, and they will have a key role in PIANC forthcoming strategic plan, and therefore in our future. We have also recent good news about PIANC growth and improvement. The national section of Brazil, that before was a qualified member, has been recently set up, and this was signed in a memorandum of understanding last 24th November in Barcelona, where I stayed with the first delegate and also with the new secretary of the association that will undertake the day-by-day of the Brazilian national section. We signed also a memorandum of understanding with HTG, the German Port Technology Association, for cooperation and technological exchange. As you can see, we are sailing ahead following the title of our newsletter. I wish you to have all you on board of our activities. I hope I will see you soon in your biennial technical visit at Fort Lauderdale in April in Florida, where I hope many, many young professionals will meet. And well, being this a virtual event, I cannot say safe return home. However, I wish you a safe computer or other device turned off. Thank you very much for your attention.
Thank you, Francisco, for the closing words. Thank you for being us today. So now it's time to announce the best speaker. I think we are doing the maths.
It take just a few seconds, I hope.
If not, we can announce later. Let's wait 1 minute. Okay, I think we have the winner. Sorry for the waiting time. So the winner is Nerea Palacios. So congratulations, Nerea.
Thank you very much.
You will receive diploma issued by PIANC.
Thank you.
Congratulations and enhorabuena.
Gracias.
And also, I wanted to thank all the speakers, all the jury members, story catchers, and the organizing team, Rocio, Bianca, Amir, Sei, and Jose. It was a great experience to work with you this year, and I hope we can see you next year in the next event.
In the third edition.
Thank you very much for all the attendees.
Thank you, team.